Today we're talking about linear approximation, and basically what that means is we're going to use a tangent line to approximate values of a function near the point of tangency. So the first ingredient is we're going to write a tangent line, and then we're going to plug in an x value. So I'm going to suppose that f of x is x to the third plus 3x squared. Then I'm going to use the line tangent to the graph of f at x equals 1 to approximate f of 1.1 and f of 0.99. All right, so I need a tangent line. So I need a point, and so the point is going to be x is 1 and y is 1 to the third plus 3 times 1 squared is 1 plus 3 is 4. To get the slope, I'm going to take the derivative. And then I'm going to plug in 1. And that's going to be 3 plus 6 is 9. So my equation is going to be y minus 4 is equal to 9 times x minus 1. So as far as approximating f of 1.1, I'm going to say, well, I might even use like predicted y. For those of you that are in AP statistics, you know about that. You're right in the thick of it right now, predicting the value of y based on some information about the relationship between x and y. And that's basically what we're doing here, predicting values of y based on the linear relationship. So that's going to equal 9 times 1.1 minus 1, and then I'm going to add 4. So that's 9 times 0.1 plus 4 is equal to 4.9. And then when I'm interested in finding f of 0.99, I'm going to do the same thing. I'm going to say my predicted y is going to be 9 times 0.99 minus 1, and then I'm going to add 4. Just using that tangent line and plugging in x values. And so that's going to be 9 times negative 0.01 plus 4. So that's 4, and I'm going to subtract 9 cents, so I'll have $3.96. And now my question that I wanted to ask, the reason that we did 2 of these, is which do you think is closer to the real value of f? This approximation of f of 0.99 or the approximation of f of 1.1? 0.99. Yeah, I would agree. Why do you think that? Over there, 525.
Because 0.99 is closer to 1 than 1.1 is.
Exactly. Okay. So in general, unless the curve is really regular in some sense, if we have say a curve like that or something, and a tangent line, that went pretty well. Notice that the farther I go away from the point of tangency, the farther off the approximation is. Okay, so that will hold in general. And then in the second semester, when we approximate functions using higher order polynomials, we'll see the same thing. Okay, one thing we could use this for is we could estimate values of square roots or cube roots or something. So I'm going to estimate the values of square root of 26 and the third root of 26 using linear approximation. And so what I'm going to do is I'm going to use the function for square root of 26, I'm going to say f of x equals square root x. And the point of tangency I'm going to use is 25. And because I know what f of 25 is. So at the point 25, 5. So I'm going to write down a tangent line. So the point is 25, 5. The slope is going to be 1/2 x to the negative 1/2. So that'll be 25 to the negative 1/2. All right, the negative 1/2. The negative 1 makes it a fraction, becomes 1 over 25. The 1/2 takes the square root, so this is 1 over 5. So that's 1/2 times 1 over 5 is 1/10. I've got a point, I've got a slope, I'm going to write a tangent line. That'll be y minus 5 is equal to 1/10 of x minus 25. And so my predicted square root of 26 will equal 1/10 of 26 minus 25 plus 5. So that's going to be 5 plus 1/10 is 5.1. And then for the third root of 26, I'm going to do f of x is equal to the third root of x, or x to the 1/3 power. So my point will be, a value of x near 26 that I know the cube root of. That'll be 27. And then the cube root of 27 is 3. Okay, the slope is going to be 1/3 x to the negative 2/3. So I plug in 27. And that'll be, 1/3 of 1 over the cube root of 27 squared. Right? My advice is always to deal with this first, the denominator, when you're taking a rational exponent, because that's the cube root, then square. Okay? So this is 1/3 of 1 over 3 squared is 1 over 9 is 1 over 27. And so the tangent is y minus 3 is equal to 1/27 of x minus 27. So my predicted cube root of 26 will be 1/27 of 26 minus 27 plus 3. Which would be 3 minus a 27th. Okay, a really common question that they can ask you on the free response section of the AP exam is, give me a linear approximation. Is it greater than or less than the true value of the function? Or is it an overestimate or an underestimate? Okay, so I'm going to just draw a picture of this scenario. Okay, I've got basically the tangent sitting above the curve is an overestimate. And that happens when the graph of f is concave up. Concave down, yes, thank you. And then over here, that's not that straight. Let me try that again. There we go, that's better. Over here, it's concave up, and the linear approximation is an underestimate, regardless of which direction off of C that we're moving. Maybe moving to the left of C, maybe moving to the right of C. Either way, it's an underestimate if it's concave up. And my recommendation is when you're faced with this question, draw this picture. Okay? It takes 5 seconds. Okay? But don't use that picture as your justification. Remember that as far as overestimate or underestimate, the reason is the concavity. That's the long and short. Okay, so this is a type of problem that we can do. There's just enough information in the statement of the question to write a tangent line, approximate the value of g of 4.9, and determine if it's an overestimate or an underestimate. Okay, so I'm going to freeze the screen and check your answer against mine in about 20 seconds. So if I take g of 5 equals 3, I turn that into a point. I've got g prime of 5 equals 2, that's a slope. And then the g double prime, that's giving me information about whether it's an overestimate or an underestimate. Okay, I write down the equation of the tangent line. I plug in 4.9 for x, and do 4.9 minus 5 is negative 0.1. I double that, I get negative 0.2. So I'm subtracting 0.2 off of 3, and I get 2.8. And then the underestimate doesn't have anything to do with what we did up above or any of that. We just look at the concavity, and we know that we're using a linear approximation. So since we're using a linear approximation on a concave up function, or at least on a near a place where it's concave up, right? We aren't presuming that g is concave up for all real numbers, but near the point of tangency, it's probably concave up, and that would indicate that it's an underestimate. All right, so this first multiple choice question actually is not in your packet, but this type of question is certainly something that could show up. I know that there's one like this out there somewhere. It's probably a secure item that I can't put in your packet. Okay. So f of 1 equals negative 1, f prime of 1 equals 2, and f double prime of 1 equals 3. Which of the following could be the value of f of 1.5? Okay, well, what we need to do is probably do a linear approximation since that's what we're doing today. So this is y minus negative 1 equals 2 times x minus 1, right? I'm using this for my point, using that for my slope. And we're interested in the value of f of 1.5. So y plus 1 equals 2 times 1.5 minus 1. Okay, so right, and actually I haven't been doing this throughout the video, but I probably should say approximately equal to, right? Okay, so that's 1, and I'm going to subtract 1, so y is approximately equal to 0. Okay, so you're going to want to choose C, because that's the value of your linear approximation. But what is the answer actually? Wait, that's supposed to be... Oh, yeah, it is. Yeah, it's D. I thought I made an error in writing the question, but it's definitely D. Why, though? Yeah, because it's concave up, meaning it's an underestimate. Okay, so this little piece of information that we didn't use would be what would keep you from getting the right answer if you didn't use it. Okay. So there you go. And if you see this, like, say, on the quiz next time, and you are choosing between, and you see it, and it looks like, oh, that's the answer I got for my linear approximation. You need to double check and make sure that you're considering the concavity. Yes, question over there, 337.
Whatever we actually call linear approximation is generally not actually the answer.
Yeah, it won't be. It can't be the answer unless the function is a line between the point of tangency and the point you're interested in, right? It's got to be something else, or unless the average rate of change happened to be exactly equal to it over, in a very rare case. That would be highly unlikely. Yes.
You're only one that's greater than?
Yes, exactly. Or I could have changed this question and said which of the following could not be the value, and I could have a bunch that were, I could have 0 and a bunch that were bigger than 1. And 0 would be the one that couldn't be. See what I'm saying? I could flip that question around also. Yes, 109. If it said which could, yes, but I see what you're doing over there. Okay, the free response, I'll show you what I was thinking about working, but we're just not going to have enough time in this class. Was the first one on the free response packet, 98, AB4, then 2013, AB6. And I think I might actually work these right now. Okay, this first one is from 1998. It's AB number 4. So we've got a function, they give us a point, and they give us the slope. So find the slope of the graph at the point where x equals 1. So we know that at the point where x equals 1, y is equal to 4. And so the slope is 3 times x squared plus 1 over 2 times y, which is going to be a half. Okay, that was pretty straightforward. Okay, next we're going to write an equation of the line tangent to the graph of f at x equals 1. So that will be y minus 4 is equal to half of x minus 1. And we'll use it to approximate f of 1.2. So we're going to plug in 1.2 for x. Okay, so that'll be y equals 4 plus half of 0.2 is going to be 4.1. Yeah, easy enough. And then we've got one from 2013 where they give us dy dx, and they're saying y equals f of x is the particular solution that passes through 1, 0. That just means that f of x is a function that has that derivative, okay, that they're giving us. So we're going to write an equation for the line tangent at the point 1, 0. You're going to use the line tangent to approximate f of 1.2. So I'll do that one more time. So the slope dy dx at the point where x is 1 and y is 0 is going to be e to the 0 times 3 times 1 squared minus 6 times 1. So that's 3 minus 6 is negative 3, so it's negative 3e. Okay, so the line tangent is going to be y minus 0 is equal to negative 3e times x minus 1. And then the approximation would be, well, the y is going to be approximately equal to negative 3e times 1.2 minus 1 plus 0. And that's a number. That's a safe place for us to stop. No, I lied. I've got one more. Okay, so this one's from 2015, and we're going to find the second derivative of y now. Okay, so we're going to say that for part B, the second derivative of y with respect to x both times is 2 minus dy dx. But they want it in terms of x and y, so that's going to be, I'm going to drop this down here, 2 minus 2x minus y. Okay, that's an expression for the second derivative of y with respect to x both times. Determine the concavity of all solution curves for the given differential equation in quadrant 2. Okay, we can do that. Quadrant 2. That means that x is negative and y is positive. Okay, so that means I'm going to analyze the second derivative. It's going to be 2 minus, okay, 2x is going to be a negative number, and y will be a positive number. So minus a positive number. Okay, so I feel like there's something I'm missing here, but it does appear that this is going to be something negative. 2 minus dy dx. Well, I'm pretty sure that we're going to be... Oh, we're subtracting a negative. Okay, so it's 2 minus a negative number is positive, so it's always concave up. Okay, I haven't worked this one in quite a while. So does f have a relative maximum, minimum, or neither at x equals 2? Okay, what we're going to do is we're going to plug in x equals 2 and y equals 3 to dy dx. So that's 2 times 2 is 4, minus y is 4 minus 3 is 1. Since dy dx is not 0, we conclude that it has neither a relative maximum nor a relative minimum. Okay, and that's all I've got for you.